Hello, everybody. This is Sunday. It's November 6th, and we are headed into week 11 of our online astronomy course. Now, Module 11 is the third in our series of 3 modules about the lives of stars. And that means that after Module 11, the week after that, you'll have your third exam. That exam opens on Monday, the 14th of November, and closes the following Sunday, November 20th. So just to let you know that that is something that's going to be coming up. But Module 11 is all about the lives of the stars, how stars are born, how they live their lives, and how they die. And this process that stars go through as they are born, live, and die, the changes that a star undergoes is called stellar evolution. Now, evolution in biology means the changes that occur within a species as generations after generation of these individuals are born. And as the individuals are born, small genetic differences arise, and those that are favorable for the animal's survival tend to become prevalent in the population, and those genes that are against the survival die out. And that way, the characteristics of the species and new species can arise. Now, that's the definition of evolution in biology. But in astronomy, stellar evolution means the changes that a single star undergoes during its lifetime. And so, that's what we're going to find out about in this module: how stars are born, how they live, and how they die. So how are stars born? Well, stars are formed from a huge cloud of gas and dust. You can see these all over the galaxy. In fact, you can see places in our galaxy and in other galaxies where stars are being formed today. So star formation wasn't something that happened long ago in the past. It's ongoing and continues throughout the universe. But how are stars formed? Well, there's a large cloud of gas and dust, and that cloud of gas and dust slowly collapses under its own gravity. And if you compress a gas, it heats up. So the center of that globule of gas gets hotter and hotter and hotter and hotter, until eventually nuclear fusion reactions begin in the center of the star. And for young stars, that is the conversion of hydrogen into helium, called helium burning. Now, when astronomers say burning, they don't mean, just a reminder, they don't mean burning the way wood burns in a fireplace. Wood combines with oxygen, and that's called combustion. That's not what astronomers mean by burning. Astronomers mean nuclear fusion reactions. So how big can stars be? How small can they be? And it turns out there's a limit, because if a star doesn't have enough mass, the center of that cloud never gets hot enough to begin nuclear fusion reactions. And that happens, the smallest mass a star can have is just a little bit under a tenth of a solar mass. It's really around 0.08 solar mass, roughly. Can stars be huge, supermassive? Well, not really. If a star gets really massive, and by really massive, I mean like 100, 150, 200 times the mass of our sun, 200 solar masses. Those stars are so bright and so hot that they just blow off their surface layers. And that huge mass loss brings them down under the limit of 1 or 200 times the mass of the sun. So there's a certain range of masses that stars have when they're born. Now, all stars are born on the main sequence of the Hertzsprung-Russell diagram, on the HR diagram. And remember, that's 89 or 80 to 90% of the stars we see in the sky today. And what all those stars have in common is that they are changing hydrogen nuclei into helium nuclei through nuclear fusion in their centers. Now, if you have a star that's sort of a low-mass star like our sun is considered a low-mass star. But if a star has a mass of about 1 solar mass or less, it converts hydrogen into helium using the proton-proton chain. And remember, that's when you have 4 protons, 4 hydrogen nuclei. They come together, they fuse together, and they form 1 helium nucleus. Now, stars that are a little bit more massive than the sun, up to the most massive stars, those more massive stars than our sun, combine hydrogen into helium using another method, and that's called the CNO cycle. CNO for carbon, nitrogen, oxygen. What happens is that the 4 protons, it still involves 4 protons fusing into 1 helium, but what happens is that the protons hitch a ride on carbon nuclei, on oxygen nuclei, on nitrogen nuclei. And they ride on those, they catch a ride on those, and that brings them together. And then the helium nucleus is ejected. That's called the CNO cycle. So one way or another, that's what stars do. They change hydrogen into helium during most of their lifetimes, and that is on their main sequence lifetime. Now you might wonder, how long will a star live on the main sequence? How long can it keep burning up hydrogen? It doesn't have an infinite supply. Well, our sun can continue burning hydrogen into helium for about 10 billion years. How about more massive stars? These massive stars, as you know, these are at the upper left-hand side of the Hertzsprung-Russell diagram. Those stars are very bright. They give off lots of energy per second. And that means they're using up their nuclear fuel very fast. Yes, they're more massive. They have more fuel, but their huge luminosities just use up that fuel like crazy. And so they have very, very short lifetimes, like perhaps 15 million years instead of 10 billion. How about a very low mass star, like an M star on the spectral types? Remember OB, AF, GK, M? M are the least massive stars. And those stars will spend 200 billion years on the main sequence. Now, our universe is only a little over 13.6 billion years old. And so there's been no time for those stars to finish their main sequence lifetime. So every M star that has ever been born is still on the main sequence of the HR diagram. But what happens when the nuclear fuel runs out? Well, first of all, why is nuclear fusion even necessary in the center of the star? Well, remember that gravity is pulling all of the star's material, all of the star's mass, trying to pull it toward the center. What holds it up? It's the pressure generated by these nuclear fusion reactions. And this balance between the inward pull of gravity and the outward push of the star's interior pressure generated by the heat of these nuclear fusion reactions, that balance between gravity inward and pressure outwards is called hydrostatic equilibrium. And so a star's job throughout its life is to maintain hydrostatic equilibrium. So how will the sun do this? A low mass star. Okay? A low mass star, when it uses up all of its hydrogen, as much hydrogen as it can use. Now, it can't use up all of its hydrogen because it has to be in a region, that hydrogen has to be in the hot central core of the star, where it's hot enough for nuclear fusion reactions to take place. But when all that hydrogen gets used up, what happens is that the pressure drops. And so the center of the core, the center of the star collapses slightly. But that drives the temperature up, and that makes it hot enough to fuse the helium that has been created into oxygen and into carbon. And so this is how carbon is made, and oxygen, by the fusion of helium. Now what happens for the fusion of oxygen? Oxygen has 12 particles in its nucleus, and the helium has 4. It has 2 protons and 2 neutrons. And so what happens is that 3 heliums come together to form an oxygen nucleus. 4 will come together to form a carbon nucleus. And that formation of an oxygen nucleus is done through a reaction called the triple alpha process. Now, an old name for a helium nucleus, the 2 protons and the 2 neutrons, the old name for that was an alpha particle. Because they were first discovered, nobody knew what they were. They were, mysterious. Today we know it's just a helium nucleus, but we still go by the old name of alpha particle. And so the triple alpha process is what is creating oxygen inside of stars, and add in another nucleus yet, and you get carbon out. Now, the triple alpha process is really temperature sensitive, and so it burns hotter than the proton-proton chain. And that means that there's more energy being released. And so the star becomes brighter. And because of that energy release, its surface swells up a bit. And so its outer surface layers cool off and become redder. That means that as the sun moves in the Hertzsprung-Russell diagram during its lifetime, in general, it's going to be carried to the upper right corner. And remember, its surface is becoming greater and greater and greater. And so it's moving into becoming a red giant. And as it does so, the surface of the sun will move past Mercury, swallow up Mercury, move past Venus, swallow up Venus, and will just come to Earth's surface. There will no longer be life possible on Earth's surface. All of Earth's oceans will have evaporated away. It will be extremely hot on the surface. And, don't let that ruin. It's not going to ruin your summer vacation. This is, let's say, 4 or 5 billion years in the future, but it's going to happen. And hopefully by that time, if humanity is still around, that humankind will have moved out to other locations, perhaps around other suns. So now when a low mass star becomes a red giant, there's some things that can happen to it. And what happens is that low mass stars, fairly low mass stars, can begin to pulsate. That is, they rhythmically expand and contract. And as they do this, they become brighter and dimmer and brighter and dimmer. And you can watch these pulsating stars do this. And our sun will become something called a Mira variable star. Mira was in fact the first variable star ever discovered. Mira means the miraculous, because they found this star that was in the sky. This was, hundreds of years ago. The star was in the sky, then it would disappear, then it came back again, and would disappear again and come back again. So they named it Mira, the miraculous. Now, let's leave the sun for a second. Let's talk about other stars. What happens to more massive stars? Well, those stars too will run out of the hydrogen in their central core where the nuclear fusion is going on. They too can change helium into carbon and oxygen. Now, if a star is hot enough, it can start also undergoing nuclear reactions where oxygen and silicon and magnesium and all sorts of heavier elements are created inside of stars. And that is where a lot of the heavy elements that we are familiar with on Earth are created. I mean, the basis of life are generally considered to be 4 elements. There's carbon, nitrogen, and oxygen, and hydrogen. The hydrogen came from the original Big Bang. The other 3 of those were manufactured inside stars. So you are made literally of star stuff. And I'm not talking figuratively here or, oh yeah, but literally that is where your carbon, if you write with a pencil, the carbon in that lid came from inside a star. If you have a diamond ring, the diamond in that made of carbon came from inside a star. All of the carbon, all of the carbon, oxygen and nitrogen in your body came from inside a star. Because after all, I mean, where did your physical body come from? Right? I mean, yes, you were born. Okay, so it came from your parents. Okay. But where did the material in your growing body came from? Well, it came from the food you ate and the air you breathed. Where did that come from? That food was grown from the ground and from elements in the air. Where did that come from? That was carried inward as the solar system formed 6 billion years ago when a huge cloud of gas and dust collapsed. Where did the elements in that huge cloud of gas and dust come from? From the interiors of stars. And so I'm speaking quite literally. I said that you are made out of star stuff, out of stardust. So let's stop the story here just for a second, because I want to mention a really very important stage that some stars go through. Not all stars, but mostly the least massive stars go through during their evolution. And that is as when they are giant stars. I've talked about how they can pulsate as mirror stars, but they can pulsate also in another way. Again, expanding, dimming, compressing, heating, very rhythmically. And these type of stars are called Cepheid variables. And Cepheid variables have a remarkable property. And that property was discovered about 100 years ago. In fact, almost exactly 100 years ago by a person who is actually my astronomical hero. And it's a woman who lived and worked at Harvard Astronomy, at Harvard Observatory. Her name was Henrietta Swan Leavitt. And she was studying these Cepheid variable stars in one of the Magellanic Clouds. And the Magellanic Clouds are not clouds. They are small irregular galaxies that are in orbit around our own Milky Way galaxy. But she was studying them. And she noticed something really amazing because she was timing how long it would take the star to go through one bright, dim, bright cycle. And that is called the period of the star, and it's measured in days. And she found out that told her the absolute magnitude of the star. And remember, a star's absolute magnitude, that's the capital M. The star's absolute magnitude tells you how bright a star would be if it were 10 parsecs away. So Henrietta Swan Leavitt came up with a period luminosity relation between a star's pulsation period and a star's luminosity, its absolute magnitude, in other words. And let me show that to you. Here it is. This is from your introduction. And this is the period luminosity relation for Cepheids. Please take a look at this introduction. There's a lot of important stuff in it. But here's how you use it to find the distances to to very distant objects in the universe. Let's say that you watched a Cepheid variable star as it went dim, bright, dim, and its period was 20 days. Okay, here is Henrietta Swan Leavitt's period luminosity relation. And in fact, more recently, very recently, it's been renamed the Leavitt law. I'll still call it the period luminosity relation for now. But let's say it was 20 days. So I go down here. The period is on the horizontal scale. Here's 20 days. And I'll go straight up from 20 days until I hit the graph of the line. Then I go over to the left, over to the absolute magnitude scale. I see the absolute magnitude of that star is -5. Now, remember, I can also just look at the star and I can measure the star's apparent magnitude just by how bright it is, how bright it appears to be in the sky, dimmed by distance. And that's called little m, the star's apparent magnitude. So I know the absolute magnitude, capital M, from Henrietta Swan's period luminosity relationship, the Leavitt law. And I know the star's apparent magnitude just by looking in the sky. That means I can use that relation that I showed you last week to find the distance in parsecs using this formula, 10 to the power of little m minus capital M plus 5 over 5. And down below, there'll be examples of how that works. I think you'll find it very, very simple to use. But this is the greatest gift ever to astronomy. There would be no modern astronomy without the Leavitt law, without Henrietta Swan Leavitt's discovery. And to my mind, it is the greatest discovery ever in astronomy. And this is how we know where we are, where our sun is in our galaxy. It's how we know there are other galaxies. It's how we know how far away other galaxies are. And even today, when we've found other methods that go somewhat farther, this is the basis of all large and very, very distant measurements to celestial objects like galaxies that are very far away. So this is a big deal. So please take a look at the Leavitt law. Now, what's going to happen to our sun? Let's come back to our sun. Remember, our sun is a Mira variable star. It's pulsating. What's going to happen is that those pulsations are going to eject the star's outer layers. Just like that. Not an explosion, just a puffing off. And it's going to look just like this picture behind me, because this is what happens when a low-mass star ejects its outer layers. It forms something called a planetary nebula. Now, a nebula is just a big ball of gas. And it's called a planetary nebula because the first astronomers to look at them through crude telescopes said, oh, look at that, it looks like a planet. They couldn't tell what it really was, a big ball of gas. But that is what happens to those outer surface layers. What happens to our sun itself? Well, all that's left behind is the core of oxygen and carbon. And this carbon-oxygen core, what supports it? Why doesn't it just collapse? Well, all the time we've been talking about the evolution of a star. We've talked about the different sorts of atoms that are inside of it. But remember, when that cloud of gas and dust began to collapse, these were atoms that had electrons with them. What happened to the electrons? Well, they've just been riding along, not doing much. They've been fairly unimportant for most of the star's lifetime. But here in the end, they're vitally important. because electrons are particles that obey something called the Pauli exclusion principle, discovered by Wolfgang Pauli, a German scientist. And the exclusion principle says something that really seems very reasonable. It says that you can't have two electrons occupy the same space at the same time. And so what happens is as this core of carbon and oxygen tries to collapse, the electrons get squeezed tighter and tighter together. And they resist that with a pressure that doesn't come from heat or anything. This pressure just comes from the pure squeezing. And that the tighter you squeeze, the faster the electrons go, and that creates a pressure that holds up the core. And that is called an electron degeneracy pressure. And the word degeneracy just means that the electrons are trying to occupy the same place at the same time, but can't. And so electron degeneracy pressure is supporting this core of a star like our sun. This is what's going to happen someday to our sun. It's going to become a white dwarf star. And this star right here in the center is a white dwarf star. That is the future history of our sun, the ultimate fate of our sun. Now, white dwarf stars, there's no fusion going on. It's purely electron degeneracy pressure. And as the star cools off, it just stays the same size. But what happens is that, remember, this is what's in the core here. This is the core of carbon and oxygen. And that carbon takes on a crystalline structure. And it becomes like a diamond floating in the sky. So this is going to become, it's about the size of the Earth. This is going to become an Earth-size crystal of carbon floating in space. And that is the ultimate fate of our star. How about more massive stars? Well, here it really gets interesting. Remember, I thought that was pretty interesting, actually. But this stuff is just incredible to my mind. But what happens in a more massive star? Remember, we talked about how they start fusing together heavier elements, how oxygen and carbon, they come together to form silicon and magnesium and neon and ultimately iron. But iron is the end of the fusion chain. You know, with nuclei that are less massive than iron, you can bring them together, and that releases energy that can provide the pressure support that supports the star. But once you reach iron, you cannot, it takes energy, you absorb energy by forming heavier nuclei, you don't release it. And so iron is the end of the fusion chain. Then what happens? Well, then what happens is that the center of that star begins to collapse. And even electron degeneracy pressure can't support the star. It turns out that the most massive white dwarf you can have is 1.4 solar masses. That was discovered by an Indian astrophysicist named Chandrasekhar, and the name of that is called the Chandrasekhar limit. That is the limit of 1.4 solar masses, the most massive white dwarf you can have. Now we're talking about more massive stars collapsing, and the electron degeneracy pressure can't hold up the core. It's greater than 1.4 solar masses. So that core keeps collapsing. And it keeps collapsing until neutron degeneracy pressure sets in. What happens is that in the very core of the star, that the nuclei of silicon, magnesium, iron, all those dissolve, and they combine, and the resulting protons combine with the electrons to form neutrons. And so you get a big ball of neutrons about the size of Earth. Pure neutrons. And that is very dense. And what happens is that that neutron center forms for these massive stars. The outer layers are still falling in. They hit that neutron, big ball of neutrons, and they bounce off. And that explosion, that bouncing, causes an explosion that is called a supernova. And so massive stars are going to end their lives as supernovas. Now, there's one more thing that can happen, and it still involves a supernova. Remember, the outer layers of that massive star have collapsed. There's a big ball of neutron that forms. In fact, that big ball of neutrons is not all that big. It's maybe about the size of Ogden City. And the outer layers come in and bounce off. Well, it may happen that even neutron degeneracy pressure fails. There's a limit of around 3 solar masses, and if that central mass is more massive than 3 solar masses, even neutron degeneracy pressure can't support the core, and it collapses all the way, total gravitational collapse, to become a black hole. And so black holes are also formed by these aging, most massive stars. Black holes, you'll find out, are real objects. We have definitively seen them. Can't see them directly, of course, because they emit no light. Black holes are very, to common sense, they're really the most amazing thing, I think, in the universe, because it is all the mass of the star collapsed down to a single point. Now, there is a distance around that single point, a radius around that single point, where the escape speed from that black hole equals the speed of light. And that's called the Schwarzschild radius, after Karl Schwarzschild, who first derived it using Einstein's equations of general relativity back in the early 1900s. But nothing can escape from inside that Schwarzschild radius, and that surface around the black hole, defined by the Schwarzschild radius, that surface is called the event horizon. And nothing inside the event horizon can ever get out. It just cannot happen. And so it is literally a black hole in space. Anything that goes in can't come out again. Also, at the surface of a black hole, if I was to drop let's say I had a big clock and I could see it from a great distances, throw it into a black hole, that clock, as you get very close to the black hole, very close, would slow down, would run slower and slower and slower, and finally it would stop right at the event horizon. And so time stops at the event horizon. This is for a non-rotating black hole. So incredible objects. I mean, what does that even mean? But it is all described mathematically, and the mathematics has been recently tested in an amazing way. And I'll be telling you about that in just a second here. So 3 final ends to a star. The least massive stars like our sun will end up by ejecting a planetary nebula and become a white dwarf star like this one. So white dwarf stars. A more massive star could undergo a collapse of its core to form a neutron star. And finally, the most massive stars could undergo a total gravitational collapse to become a black hole. So, these objects can do all sorts of tricks, especially if they're in a binary star system. So if you have a neutron star, a white dwarf, or a black hole in a binary star system where you have the black hole, white dwarf, neutron star, whatever it is, being orbited by a normal star, the terrific gravity of that collapsed object, that white dwarf, neutron star, black hole, can pull gas off of the companion star. And that gas can collect on the surface. And if it's a white dwarf, that gas can collect on the surface And that hydrogen gas that it's pulled off can heat up and explode as a nova. Not a supernova, that's the whole star exploding. This is just a nova, gas exploding on the surface of a white dwarf. A neutron star can really, I think, do some amazing tricks. Now, it too, if it is in a binary star system, it can pull gas from its companion star and do all sorts of things. I won't go into those, but those are listed in the introduction to the course module. But I told you how small these stars are, right? The white dwarf is about the size of Earth, roughly. Neutron star is about, let's say maybe 10, 15 kilometers in radius, probably closer to 10 kilometers in radius, about the size of Ogden City. And think about an ice skater. Boy, that's a transition. Think about an ice skater here, and she's going to do a scratch spin. What happens as she pulls in her arms? That spin goes faster and faster and faster and faster until she's really turning. Well, the same thing happens to the neutron star. I mean, it's gone to something about the size of the Earth, how the core was before the collapse, to the size that is many, many, many times smaller. So it's going to really be spinning around fast. And at the same time, these stars have magnetic fields. All stars have magnetic fields. We haven't talked much about them, but they all have magnetic fields. But as the star collapses, that magnetic field gets concentrated. And so I have a rotating, very powerful magnet. And that acts like a lighthouse and sends out light. And that light can be in the form of radio waves. It can be in the form of light waves. It can cover a large range of the electromagnetic spectrum. And most of these we may never see because it's acting like a lighthouse, and maybe the lighthouse never sweeps past Earth. But if here's the beam of this rotating magnetic neutron star, that is called a pulsar, and because it pulses. Because now, right here, it's pointed towards you, toward the screen. And so if this was, my finger was the beam, you'd receive a pulse. And then the pulse moves away. And here you receive another pulse, and another pulse, and another pulse. And receive a pulse each time this rotating neutron star goes around once. It's called a pulsar. And the first one was discovered by Jocelyn Bell in the 1960s. We since know of many of these, and in fact, we even use them for navigation. They are tremendous clocks. You could set the pulsation, the time for one to go around once is so well determined that you could easily rival the best atomic clocks. And so these pulsars are really just fascinating objects. We've discovered, how do we see black holes if they don't emit any light? Well, again, if they're in a binary star system, you might have a black hole, then you have another star going around it. The black hole pulls off energy. That energy forms a disk of gas around the black hole and slowly spirals in. And as that gas spirals in, it heats up. And as that gas heats up, it can give off all sorts of radiation, X-rays, for instance. And that's how the first black holes that were found were discovered, by the X-ray emission from them. One final thing that can happen in a binary system that is, I think, the most amazing thing of all that we've been able to detect. That is, you could have two black holes orbiting each other, and they can collide with each other. They merge into a single black hole. And that is such a violent event. It shakes the structure of space and time. This sounds like science fiction. I promise you it's not. It shakes the structure of space and time and sends out waves. And those waves have been detected on Earth. And so we can measure the size of the individual black holes in that system by looking at the gravitational waves that come off of these merging compact star systems. Right now, there are 3, and I think one more is coming online. 3 gravitational wave observatories in action, 2 in the US, I think 1 is in Europe, and I forget where the 4th one is going to be starting up. This is a tremendously exciting thing to happen in astronomy. And my favorite merger that we've seen are 2 neutron stars that go around. 2 neutron stars that came together and merged together. And that created such an explosion that we got the gravitational waves. We told telescopes to point to that part of the sky, and they got a huge flash of gamma rays from this merging binary neutron star system. And what they found were the gamma rays given off by new elements that were being created, elements like gold that were being created. And in fact, the heaviest elements, those in the periodic table, were created by the merger of neutron stars. So if you have a piece of gold jewelry or necklace, a ring, whatever, every atom of gold in that came from a merger of a neutron star. Well, almost all of them. There's another astronomical source that creates a bit of it, but the primary source of all the gold that you may have is merging neutron stars. So you can see the life and death of stars is absolutely fantastic. It is one of the most amazing tales in all of astronomy. So that tale ends our 3 modules on the stars. And next module, we'll start talking about how stars are arranged into galaxies, how galaxies are arranged, and where did this whole universe come from? What's it made of? Some of the biggest questions that we can imagine. But to get down to the more mundane, I do want to show Stellarium to you. So let me just pull up Stellarium here. And here's Stellarium. This is at 3:59 a.m. on Tuesday morning, November 8th. Now, I know you're probably not going to be up on 3:59, but if you're up and the sky is clear, go on outside, look in the west, and take a look at the moon. Now, I'm going to zoom in on the moon, and you can see it's a deeply red moon. That's because this is a lunar eclipse. It is a very deep one, meaning that the moon is deep inside Earth's shadow. And 3:59 a.m. is when, in the morning, it's going to be at its maximum. I'm going to back up here and just go an hour earlier. Here's 2:59. Let me drag that to the center. And you can see the moon is just moving into Earth's shadow at 2:59. And let me move an hour after maximum, 4:59, and I'll zoom in here. And you can see the moon is just moving out of Earth's shadow. But in fact, as I said, the maximum is going to be at 3:59, and it's really going to be a spectacular lunar eclipse. Now, the forecast is not encouraging. The forecast is for it to be overcast that night, so we might be out of luck for this one, but I hope not. Wake up, take a quick look outside, and if you can see stars, go on outside and take a look at the moon. Totality lasts for about 40 minutes on either side of 359, but it's best around 359. Now, in this module, I've included a link right under the video that'll take you to a site that will describe the lunar eclipse in Salt Lake City in a little bit more detail. Well, I hope you have you'll find this module as fascinating as I do. As I said, it's some of the most interesting material, I think, in astronomy. It incorporates some of astronomy's biggest discoveries. And I hope you enjoy learning about it. And just as another reminder, your third exam will open up not tomorrow, Monday, not tomorrow the 7th, but a week after that, Monday the 14th, your third exam opens up. It closes on the next Sunday, the 20th. So good luck on that. But before that even opens, I will see you next week. So I'll look forward to that and say goodbye for now. Bye-bye.